What would happen if you could travel to the other side of the universe? A place where light has never reached, where time can flow backward, and every grain of dust carries within it the memory of creation. We have always believed the universe to be infinite, but what if it is merely a closed loop, a vast mirror reflecting itself on the other side? To reach that boundary, everything must begin with a single moment, a bold experiment to open the first doorway through space and time. They called it the Wormhole Test. And now we will explore together the history, theory, and tragedy of the wormhole, the tunnel of space and time, from the grand scientific dream to the ultimate limits of the cosmos. For years, scientists had refined the equations of general relativity, learning to twist space-time in simulations as if it were a sheet of silk. And then came the breakthrough: a contained wormhole stable for fractions of a second in a vacuum chamber near the moon's orbit. It was small, invisible, but its gravitational signature was undeniable. Space itself had bent. For the first time in history, the cosmos had blinked. Encouraged by success, they expanded the scale. Massive superconducting rings orbiting Neptune acted as anchors, their magnetic fields shaping a gravitational funnel almost 4 billion kilometers long. From Earth, it looked like a ripple in empty space, an invisible current running through the dark. But through instruments, it was poetry. Two mouths of space-time perfectly synchronized, their throats humming with curvature. At last, the dream of interstellar travel felt near, no longer a matter of rockets or fuel, but geometry, a door made not of matter, but of math. The equations promised that if curvature could be maintained long enough, a ship could step across the galaxy in the time it takes to draw a breath. Every simulation said the same thing: it should work. No one noticed the subtle warnings buried in the data, the faint asymmetries, the invisible tension accumulating across the bridge. It was like stretching glass that looked smooth until the final fracture line appeared. But in the pursuit of discovery, curiosity often moves faster than caution, and so the test proceeded. The first manned vessel, Aletheia One, approached the mouth of the wormhole at 400 hours. Its hull reflected the dim sunlight of Neptune's rings, its engines silent. Inside, the crew recorded the last normal telemetry humanity would ever receive. They activated the field. The ship crossed the event horizon, and then nothing. The signal did not break. It stretched. As if time itself had turned viscous, light slowed, and data began to smear across the transmission. The ship's image froze, hovering halfway through the tunnel, its structure caught in a distortion that no one could explain. On the other side, near Neptune, sensors still detected the wormhole's exit mouth, and inside it, faint, distant ghost-like, was Aletheia One. Visible, but unmoving. It was supposed to emerge within minutes. Instead, hours passed, then days, then years. The ship was still there, but it never arrived. They waited. The team on Earth continued to monitor the field. The wormhole's energy fluctuations stabilized after the crossing, as if the system had frozen in equilibrium. Yet the ship remained suspended. From one end, it appeared to crawl forward. From the other, it never moved. It was the universe's first paradox made visible. High-speed analysis revealed something even stranger. The clocks aboard Aletheia One, still faintly transmitting, ticked slower than expected, but not by relativity alone. Their time dilation exceeded all predictions. According to general relativity, the delay should have been milliseconds. Instead, it stretched into centuries. After the first decade, humanity gave up hope of contact, but the wormhole remained open, a silent wound between the planets. Telescopes kept their eyes fixed on the distant shimmer near Neptune, where the ship's distorted reflections still glowed like a trapped ghost. Every few years, new data was captured, subtle shifts, a faint oscillation, the ghost moving a fraction closer. Mathematically, it was still advancing, at a rate so slow it defied comprehension. Extrapolations suggested a horrifying number: at this speed, the ship would take 500 years to fully cross the throat. The crew long dead would arrive centuries after their own launch, their voices echoing into a future that no longer knew them. The experiment had succeeded in creating a bridge, but it had failed in creating a passage. The physicists faced an uncomfortable truth. General relativity, the grand equation that had carried them this far, did not account for what they had seen. It could describe the curvature, but not the consequences. It predicted the tunnel, but not its cruelty. Something inside the mathematics was missing: a term, a symmetry, a secret. and in its absence the universe had responded with silence. The project was abandoned. The wormhole was sealed. But data continued to drift in for decades, a heartbeat from across time growing fainter but never fully gone, as if the bridge itself refused to die. When the remains of Aletheia One finally emerged 5 centuries later, it was no longer a ship. It was a hollow relic, scarred by radiation, its structure aged beyond measure. Inside, the crew were statues perfectly preserved, their bodies untouched by decay, as though time itself had been diluted around them. Every watch on their wrists still ticked, but no two showed the same hour. The data recorders were still functioning. The final transmission they contained was a single phrase from the captain, barely audible. We saw ourselves ahead, moving backward. Physicists dissected every bit of information. The gravitational distortions, the time differentials, the energy fields. Everything pointed to the same impossible conclusion: the wormhole had not failed mechanically. It had failed conceptually. Relativity predicted that spacetime would bend smoothly between two mouths. But what if spacetime itself rebelled against being folded that way? What if the universe enforces not just laws of motion, but laws of meaning, preventing causality from looping upon itself? This idea, once philosophy, became physics. The chronology protection hypothesis, later proposed by Hawking, would formalize it decades later. But its first evidence had already been found, not in theory, but in the shattered hull of Aletheia One. The mission proved a devastating lesson. Einstein's theory, magnificent as it was, might not be the whole story. It could explain the curve of gravity, but not the conscience of space-time. There were limits built not of numbers, but of logic boundaries the cosmos refused to let us cross. Was it the failure of mathematics or a success of nature defending itself from paradox? No one could answer. Some whispered that the wormhole had not collapsed at all, that it had branched into another domain, another layer of reality, one where time flows differently. Others argued that the universe had simply closed the loop to protect its own consistency. But one truth became undeniable: if the laws of physics form a language, then the wormhole was a question the universe chose not to answer. From that moment on, the tone of humanity's ambition changed. Exploration gave way to humility. The stars still called, but their light now carried a warning. Every failure in physics is a kind of revelation. It shows not what the universe forbids, but what it values. Perhaps the tragedy of Aletheia One was not a mistake, but a message. That shortcuts through space-time demand a price not of technology, but of understanding. That before we bend the universe, we must first learn why it resists. And so, the story of wormholes did not begin with triumph, but with loss. A ship swallowed by silence, and a question that still echoes between the stars: can space be crossed without crossing the boundaries of truth itself? Every era begins with a question. Ours began with a simple one: what is space? For centuries we treated it as emptiness, the stage on which matter performed silent and unchanging. Time, meanwhile, was the ticking of a universal clock. The two never touched. They ran side by side, obedient, separate. But the deeper we looked, the less sense that separation made. Every movement through space altered time. Every change in time echoed through space. They behaved not like two elements, but like threads of the same fabric. To tell the story of space-time is to tell the story of how humanity stopped looking at the universe as a stage and began to see it as a living thing, a woven tapestry stretched, folded, rippled, and scarred by the weight of everything that exists. And it is also a story of those who dared to imagine it before the equations were born. The poets, the dreamers, the few who looked at the stars and thought perhaps the stage is alive. This is their inheritance and ours, to understand the cosmos not only through numbers but through wonder. Before Einstein, before the equations that bent the universe, there was a poet, Edgar Allan Poe. In 1848, in a strange, almost mystical essay titled Eureka, Poe wrote, "Space and duration are one." To physicists of his time it was nonsense, but to history it was prophecy. In a century when science and art still lived apart, Poe had somehow glimpsed a union that mathematics would not discover for another 50 years. He imagined a cosmos born from a single act, an explosion of unity into multiplicity, what we now call the Big Bang. And in that vision he described time and space as inseparable reflections of one another's motion. Was it intuition, coincidence, or something deeper, the way imagination sometimes stumbles upon truths that logic has not yet found? Whatever it was, his words would echo through generations of scientists who never read his poem, but lived its idea. Half a century later, that poetic intuition became mathematics. A young patent clerk staring at the light from a clock tower in Bern began to suspect that time itself might not be absolute, that the universe did not keep one rhythm, but many. In 1905, Albert Einstein published his special theory of relativity. It began not as a discovery, but as an act of faith in the constancy of light. No matter how fast you moved, no matter how you chased it, light speed never changed. From that simple assumption, the universe transformed. Space and time were no longer fixed. They bent around motion, exchanging roles depending on the observer. A meter for one traveller was shorter for another. A second for one clock could stretch into minutes for another. The deeper you moved into velocity, the more time itself slowed its breath. Einstein's insight was radical, not because it broke physics, but because it revealed its humility. There was no privileged perspective, no true rest. Everything depended on where you stood, how you moved, and how you saw. Even the separation between now and then was no longer universal. Events that appeared simultaneous to one observer might occur centuries apart to another. Reality, it seemed, had lost its single voice. And yet, paradoxically, this chaos formed a new kind of order, a symmetry so perfect that it reshaped how we think of truth. Einstein's equations whispered something profound. Space and time are not containers for reality. They are reality. And that idea, once spoken, could never be undone. 3 years later, in 1908, Einstein's former teacher Hermann Minkowski took his students' equations and drew a revelation from them. He declared, henceforth space by itself and time by itself are doomed to fade away into mere shadows. Only a union of the two will preserve an independent reality. What Einstein had glimpsed through algebra, Minkowski sculpted into geometry. He built a four-dimensional continuum spacetime where every event, every particle, every breath of existence had its coordinates not just in space, but in time as well. In this world, the universe was no longer a sequence of happenings, but a single shape, a frozen sculpture, infinite and eternal, where past, present and future coexist as different slices of the same whole. We move through it not like travellers on a road, but like lines drawn through an already complete picture. To visualize space-time, Minkowski described world lines, the paths that objects trace through the four-dimensional fabric. A stationary stone draws a vertical line unmoving through space but always marching through time. A beam of light carves a diagonal, no rest, no pause, pure motion. Every atom, every planet, every human being leaves behind such a thread, interwoven with billions of others forming the grand tapestry of existence. This picture was more than poetic. It was predictive. Through Minkowski's framework, the relativistic effects of Einstein's theory could be seen calculated and understood geometrically. Space was no longer flat. It was curved by time. Time was no longer linear. It was shaped by gravity. And suddenly, physics began to resemble art again, not a machine of laws, but a living canvas of connections. In 1915, Einstein completed the journey. The general theory of relativity was not merely a correction, it was a revelation. It told us that gravity was not a force pulling objects together as Newton believed. It was the shape of space-time itself curving around matter and energy. Mass tells space how to bend. Space tells mass how to move. The dance is eternal. John Wheeler, one of Einstein's intellectual heirs, would later summarize it perfectly. Matter tells space how to curve and space tells matter how to move. Imagine a rubber sheet stretched tight. Place a marble on it, the sheet dips. Now roll a smaller marble nearby, it spirals inward, not because an invisible force pulls it, but because the surface itself is bent. That is gravity. Not a hand, but a shape. Every planet, every star, every galaxy warps the fabric around it, creating wells and valleys in which light and time themselves must flow. When you orbit the sun, you are not circling a mass, you're following the curve of reality. This bending of space-time does more than explain motion. It explains beauty. The deflection of starlight around the sun during an eclipse in 1919 confirmed Einstein's prediction. Space had curved and humanity had witnessed it. Reality had shape invisible but measurable, and yet in this triumph a shadow appeared. If gravity could curve space-time, could it also tear it? Could the fabric fold so tightly that the two sides of the universe touched? Could time itself twist into a loop? In the mathematics of relativity, the answers were yes. It was not forbidden. Space-time could bend not only into orbits but into tunnels, bridges between distant points, perhaps even distant universes. The theory that described the fall of an apple had by logic alone opened the door to the impossible. From Einstein's equations emerged the seeds of the black hole, the white hole, and the wormhole, three shapes that would redefine how humanity imagines reality itself. And yet in the quiet of his study, Einstein felt uneasy. He had not meant to create monsters. He had only sought elegance. But in mathematics, elegance and danger often share the same face. By the time Einstein died in 1955, space-time had become more than a theory, it had become our language for the universe. But no one could yet say what it was. Was it substance or illusion? Was it truly curved, or was curvature only a reflection of how our minds measure motion? Perhaps space-time is not a thing at all, but the shadow of deeper laws still hidden from view, a projection of something that lies beyond dimension. And if so, then every wormhole, every singularity, every cosmic equation we chase is not an end but a clue, a trace of something vast whispering that the universe is not finished speaking. General relativity is often called a theory, but it behaves more like a machine. Feed it matter, and it tells you how space bends. Feed it geometry, and it predicts how matter moves. It is a perfect loop, logical, precise, mercilessly consistent. But like all machines, it cares nothing for comfort. It produces outcomes that are beautiful, yes, but also terrifying. In the early decades after Einstein published his equations, most physicists treated them like a marvel of mathematics rather than a guide to reality. The equations worked, but their consequences seemed absurd. A universe that curves itself, a clock that slows near stars, a path where time can stop, and yet every test confirmed it. Light bent around the sun exactly as predicted. Mercury's orbit matched the corrections Einstein calculated. Gravity, it seemed, was not a force at all, but a story geometry told itself. Still, something in the equations haunted those who read them carefully. The machine produced not only elegance, but extremity. It suggested that if enough matter were compressed into a small enough region, the curvature of space would become infinite. Time would stop. Light would fail. The geometry would fold into a singularity, a point without dimension, yet infinite in consequence. The equations did not forbid it. They required it. It was as if Einstein had built a flawless instrument, and within its music, hidden between the notes, there was a scream. Physicists debated whether the singularities were real or merely artifacts, errors of overextension, the mathematical equivalent of trying to divide by zero. Surely the universe would never allow something so absurd. Surely reality would protect itself from infinity. But reality is rarely interested in what we find absurd. In 1916, only months after Einstein released his theory, the first exact solution to his equations arrived from a battlefield. Karl Schwarzschild, a German physicist serving on the front lines of World War I, had been reading Einstein's new papers during moments of calm between artillery bombardments. Despite the chaos around him, he found something that even Einstein had not. He discovered that the equations of general relativity had an exact symmetrical solution, describing the gravitational field around a static spherical mass. The result was astonishing and disturbing. According to Schwarzschild's solution, if a star's mass were squeezed below a certain critical radius, now called the Schwarzschild radius, nothing, not even light, could escape its gravity. Beyond that invisible boundary known as the event horizon, the pull of space itself would drag everything inward. The deeper one fell, the slower time would pass, until at the center time would simply end. This was no ordinary gravity. It was gravity turned inside out, a place where the geometry of space-time collapsed into a single infinite point, a singularity. Schwarzschild's equations predicted this flawlessly. They did not require new forces or hidden mechanisms. They flowed directly from Einstein's logic. And that was what frightened everyone most. When Einstein read Schwarzschild's letter from the front, he was impressed but uneasy. He acknowledged the mathematics, yet dismissed the physical reality. He called it a mere mathematical curiosity. The idea that a star could collapse into itself, leaving behind no surface, no structure, only geometry. It was too grotesque to be true. Einstein, for all his genius, could not accept a universe that allowed infinity. He believed the cosmos must possess self-correcting mechanisms, precious forces, or unknown laws that would halt collapse before it reached that point. He trusted nature to show restraint. But the equations showed no such mercy. They allowed stars to die completely. They allowed space-time to fold inward until even light could not tell the tale. The first black hole had been written into mathematics before anyone dared to name it. For decades, physicists wrestled with the ghost of Schwarzschild's discovery. Even as telescopes improved and observations grew sharper, no one wanted to believe in such monsters. The term black hole would not appear until 1967, coined by John Wheeler. Before that, they were called frozen stars, collapsed objects, or sometimes singular solutions, polite names for an unthinkable truth. Einstein himself rejected the notion to the very end. In a 1939 paper, he argued that physical laws would prevent any real object from collapsing fully into a singularity. The mathematics, he said, had reached beyond its domain. The universe, he insisted, was stable, but his insistence was no longer enough. That same year, two American physicists, J. Robert Oppenheimer and Hartland Snyder, quietly dismantled his argument. Using Einstein's own equations, they modelled the collapse of a massive star once it exhausted its nuclear fuel. The result was devastatingly simple: nothing could stop gravity. The outer layers would fall inward, the core would compress, and once it crossed the critical radius, it would continue collapsing forever, not metaphorically, not imaginatively, but literally. The event horizon would form, naturally sealing the singularity within. No force, not even the speed of light, could escape. Their paper on continued gravitational contraction was a triumph of logic and an omen of despair. But the world barely noticed. It was published in September 1939, the same week Germany invaded Poland. While humanity tore itself apart, the universe quietly revealed how stars do the same. Oppenheimer would later lead the creation of the atomic bomb, another form of collapse not gravitational, but moral. His work with Snyder was forgotten for nearly 2 decades, buried under war secrecy and guilt. When it resurfaced, everything changed. Observations of quasars, brilliant objects shining with the energy of entire galaxies, forced astronomers to reconsider. Nothing else could produce such light, such power, such hunger. And so reluctantly, physics returned to the idea it had tried to bury. The singularities were not mistakes. They were inevitable. They were real. By the 1970s, evidence became overwhelming. The centers of galaxies pulsed with invisible gravity. Stars orbited emptiness. Radio signals flickered with perfect precision, the calling cards of collapsed giants. Even Einstein's heirs had to admit it. His machine, the grandest mathematical creation of the 20th century, had predicted something beyond his control. The universe did not fear infinity, it embraced it. And yet within that embrace lay something paradoxically human, the reflection of our own limits. For the black hole in its silence shows us the boundary of understanding. It is where every equation stops working, where knowledge turns back on itself. It is the point at which the universe says, "Here your language ends." But endings in physics are never truly ends. They are beginnings in disguise, and the singularity, that absolute inescapable zero, would soon give birth to its mirror image, the white hole, and the bridge that might connect the two. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. Yet here in the heart of his own creation, comprehension faltered. General relativity, his masterpiece, had spoken a truth even its creator could not bear. It had shown that beauty and destruction are twins born from the same geometry, that the deeper we understand reality, the closer we come to the edge of reason. The black hole is not a mistake. It is the universe's memory of creation, a place where the equations we trust surrender, and what remains is silence. Perhaps that silence is not empty. Perhaps it is simply waiting for the next question. For every law of nature there exists a mirror. If gravity pulls inward, something must in principle push outward. If a black hole consumes everything, there could exist its opposite, a fountain that gives everything back. This was the question that haunted Igor Novikov, a Soviet physicist in the 1960s. Working through the same equations that had revealed black holes, he noticed a hidden symmetry. Einstein's field equations made no distinction between the past and the future. If you reverse the direction of time, the mathematics still works. And so, if one solution describes a region that swallows light, another must describe one that expels it. That mirror image object became known as a white hole, a place where nothing could enter, only leave. A black hole's perfect twin running time backward. Imagine it from within matter bursts outward faster than light could chase it. From without no force could cross its threshold. It is not a mouth, but an eruption, a permanent sunrise in reverse. To the imagination it felt like redemption, as though the universe, so obsessed with collapse, had secretly kept a mechanism for renewal. To the physicist, it was an uncomfortable truth. If Einstein's equations truly held everywhere, then white holes were as real mathematically as black ones. And if so, could the universe contain both? Could there be a cycle, a balance, where what one devours the other releases? Novikov's peers were skeptical. They saw beauty, not evidence. Yet even skepticism could not erase the equation's demand time when reversed is still time. And if nature once permitted collapse, it may also remember how to exhale. A white hole would look nothing like its dark sibling. Where a black hole hides behind a curtain of shadow, a white hole would blaze like a second sun, a wound of light too intense for the eye. Its gravity would repel, not attract. Any object drawn near would be hurled away like dust before a storm. In theory, the surface of a white hole, its anti-horizon, marks a boundary that cannot be crossed from the outside. Matter and energy can emerge, but nothing can return. Entropy flows backward. Disorder decreases. It is the universe rewinding itself. The concept violates nearly every intuition we possess. Thermodynamics demands that entropy always increase. White holes demand that it fall. For them to exist, the arrow of time would have to flip. A cup shattered on the floor would reassemble, a dying star would unburn. And yet some cosmologists have dared to wonder whether such reversals might have occurred briefly during the earliest moments of creation, when the universe was too young to obey its own rules. At the edge of the Big Bang, time may have been flexible, even reversible. A white hole might have flared then, only to dissolve as the cosmos cooled. Perhaps every act of creation leaves behind its own reflection, hidden beyond the horizon of memory. If that is true, the Big Bang itself could be interpreted as the ultimate white hole, the eruption of all matter, all energy, from a singular point, expelling not darkness but being. And we suspended in its light are still inside that burst. If black holes swallow and white holes expel, the mind cannot resist the next step. What if they are connected? The mathematics of general relativity quietly allows such a union. A black hole's singularity could in principle be linked through the folds of space-time to a white hole elsewhere, a tunnel where one end devours and the other gives. Matter falling into the black hole might not be destroyed at all, but re-emerge through the white hole's mouth in a distant region of the universe, or perhaps in another universe entirely. This idea fascinated John Wheeler and Roger Penrose. They treated space-time not as a smooth continuum, but as something that could be stitched together, folded like fabric. They imagined a wormhole, a slender throat connecting two distant mouths. The geometry was exact. The equations did not protest. In the clean, indifferent language of relativity, the bridge existed. Wheeler saw it as a playground for the mind, a way to test the extremes of geometry. He even coined the word wormhole, comparing space-time to an apple, whose surface could be shortcut by a tunnel through its core. To travel through such a path would be to cheat distance itself, to cross billions of kilometers in a single step. But geometry and reality are not always friends. The same equations that allow a wormhole also demand its instability. The connection between a black hole and a white hole is delicate, temporary. Any disturbance, even a single photon, would cause it to collapse. Still, the idea refused to die. It lingered like a melody that cannot be unheard. If the universe once folded upon itself to form such bridges, perhaps it could do so again. Perhaps the night sky hides more than stars. Perhaps behind the dark centers of galaxies, there are doorways waiting for the right question. Long before Wheeler gave it a name, Einstein himself had glimpsed the bridge. In 1935, together with his assistant Nathan Rosen, he searched for a way to remove the singularity from his equations, to smooth the infinite, to heal the tear. They found that by mathematically duplicating space-time and gluing the two regions at their horizons, they could eliminate the singular point entirely. What remained was a continuous tunnel connecting two identical universes. Einstein and Rosen called it a bridge, not a hole. To them it was a symbol of unity, a geometric handshake between mirrored worlds. It was never meant as a path for travellers, only a proof that space-time could remain whole, even when bent to its limit. The bridge's structure was elegant. Imagine two black holes back to back, their interiors joined by a narrow throat. At the instant of formation, light could in theory pass from one side to the other. But as soon as time moved forward, gravity pulled the openings shut. The bridge was self-closing. It existed for a moment, a heartbeat in space-time, then vanished. Einstein saw this as reassurance. The universe protects itself from singularity by connection, not by chaos. But later, physicists saw something else entirely. They saw potential. If a bridge could exist even for an instant, could it be stabilized? Could matter, energy, or even information be sent through before it closed? The question changed everything. It transformed Einstein's mathematical curiosity into a dream, a vision of cosmic travel-time reversal and communication across universes. The Einstein-Rosen bridge became the foundation for all later theories of wormholes, a symbol not of certainty but of permission. It said the equations allow it. Now find the courage to test them. In the end, no telescope has ever seen a white hole, no probe has crossed an Einstein-Rosen bridge. They remain possibilities, mirrors of thought cast into the void. But in contemplating them, we learned something essential about ourselves, that even when faced with the most devouring darkness, the human mind instinctively imagines a door. Perhaps that instinct is not foolishness, but memory, a quiet remembrance that the universe itself was born from light bursting through a wall of nothing. Maybe every black hole hides that memory too, and somewhere beyond its silent horizon, its twin is still shining a white hole whispering the other half of creation's story. The first wormholes were born not from stars but from equations, elegant, symmetrical, exact. They existed perfectly on paper and nowhere else. According to Einstein and Rosen's mathematics, spacetime could in principle fold upon itself, connecting two distant regions through a narrow throat. It was the purest geometry imaginable, a bridge with no material substance, a curve in the invisible fabric of existence. In that simplicity lay its temptation and its curse. When physicists tried to model a ship, a photon, even a pulse of energy passing through the structure collapsed. The moment anything entered the throat, its own gravity disturbed the balance. The curvature imploded, the tunnel sealed shut faster than light could cross. The bridge was there, but not for us. John Wheeler, who first coined the term wormhole, described the discovery with unease. Space, he said, is like a nervous system. Disturb it and it reacts instantly. To exist, a wormhole would need to balance two infinities, one pulling inward, one pushing outward. But space-time, like a living organism, does not tolerate imbalance for long. Every attempt to traverse it, even in simulation, ended the same way: collapse. The equations screamed against the act of passage. It was as though the universe were defending its own continuity, refusing to let one region touch another too directly. To many physicists, this became a kind of revelation. Perhaps wormholes are not forbidden, they are simply private. Nature allows them to exist in principle, but forbids intrusion. They flicker in the quantum foam microscopic tunnels, forming and vanishing within Planck-length scales, brief, transient, unobservable. A whisper of connection between points that never meet. To cross them would be like trying to step inside a shadow, possible only for an instant and only for something that leaves no mark. And so the problem of traversability became the first wall humanity met, not of technology but of principle. The geometry allowed a path, reality did not. If gravity barred the door, entropy locked it. The second law of thermodynamics, that disorder must always increase, is more than a principle. It is time itself written into mathematics. Entropy gives direction to existence. It ensures that heat flows from hot to cold, that stars burn out, that moments die. A wormhole, to remain open, would have to violate that arrow. It would need to take a chaotic system, space-time, in its restless equilibrium, and hold it in perfect balance. Entropy would have to stop rising or even fall, and that the laws of physics refuse. The problem deepens when you consider the mirror of the black hole, the white hole. A white hole would decrease entropy, expelling organized matter into an already disordered universe. To maintain the bridge between the two, entropy would need to flow backward on one side and forward on the other, a contradiction that tears the very logic of time apart. Thermodynamics is unforgiving. It forbids the reversal of causality. If disorder could ever decrease, memory itself would lose meaning. Events would unfold both ways, history would dissolve into symmetry, and the wormhole suspended between past and future would have no preferred direction for time. It would become a timeless corridor, a place without before or after. Some physicists, desperate to keep the dream alive, searched for loopholes. They asked, could quantum fluctuations briefly allow local decreases in entropy if the universe compensated elsewhere? Could a wormhole exist only for an instant, short enough to break the rule, but too brief for the rule to notice? Such speculation bordered on the mystical, but mathematics did not protest. At the smallest scales, the universe already behaves as though it is constantly making and unmaking connections. Particles appear and vanish, energy fluctuates, and for impossibly small intervals, causality itself seems to waver. Perhaps some thought the cosmos allows wormholes in the same fleeting way, tiny bridges blinking in and out of existence too quick for thermodynamics to forbid. But even that hope came with a cost. Such wormholes would be smaller than atoms, shorter than a femtosecond, impossible to preserve. They would open only to close themselves, a universe inhaling and exhaling in silence. And so, entropy remained undefeated. The door stayed closed not by cruelty, but by balance. The arrow of time, like gravity, insists on one direction, and through that insistence the cosmos keeps its order. When physicists modelled the dynamics of a full-scale wormhole, the results were clear and merciless. The moment the tunnel formed, even the smallest disturbance grew uncontrollably. A photon entering the throat increased energy density, steepening curvature. The narrowing continued exponentially, like a heartbeat accelerating into a seizure. Within a fraction of a second, the throat pinched off. From the outside, this collapse might release a brief flash of radiation, a gamma burst, a gravitational wave, a ripple of light marking the death of a bridge. Then silence. The geometry had healed itself. The wound in space-time had closed. John Wheeler compared this behaviour to a biological immune response. The universe, he said, rejects wormholes the way a body rejects an incompatible organ. It recognises the imbalance corrects. It restores equilibrium. The question that followed was haunting. What happens inside during that instant of collapse? Does the traveller, if one could exist, perish in infinite gravity? Or does the throat close faster than time itself, preserving a fragment of what entered trapped forever unreachable? Some theorists proposed that the collapse might not destroy information but transform it, that the data of whatever fell in matter, energy consciousness, might be encoded in the resulting black hole's surface. Perhaps wormholes don't die, they simply change their name. Perhaps every black hole we observe is the fossil of a bridge that once tried to open. It is an idea both poetic and terrifying. If true, the universe is littered with tombs of failed connections, gateways that closed too soon, remnants of attempts to unite what was never meant to touch. Every black hole, then, would be a scar, a reminder that space-time, though flexible, can still break. Even if the laws of entropy and geometry were somehow defied, even if a wormhole could remain stable, a final obstacle would still annihilate the traveller tidal gravity. Inside the throat of a wormhole, gravity is not uniform. The pull at your head could differ from the pull at your feet by billions of Gs. The difference would stretch your body like a thread, a process so violent it earned a deceptively playful name, spaghettification. As you approach the centre, your sense of direction collapses. Like curves in impossible ways, the universe around you distorts, collapsing into a single, pulsating sphere of brightness ahead. Time slows, then fragments. Your heartbeat, your thoughts, your very perception of existence smear across dimensions you can no longer comprehend. If this sounds like death, it is worse than death. It is the dissolution of the concept of you. Matter is no longer matter. Atoms elongate, subatomic forces unravel. You become geometry, a trace in curvature, a vibration written into space-time. And yet even here some scientists whisper a gentler hypothesis. If information cannot be destroyed, as quantum mechanics insists, then even in the agony of spaghettification, the pattern of what you are, your structure, your data may survive. It may be absorbed, preserved as holographic information along the wormhole's boundary. Your atoms would die, but your form might remain not as a traveller but as a shadow, a static echo encoded in the walls of space-time. Perhaps in that sense no one truly dies within a wormhole. They are translated, not across distance but across meaning, not destroyed but rewritten. It is a fragile comfort that even at the edge of impossible gravity, existence might still find a way to remember itself. By the end of the 20th century, the verdict was clear. Wormholes are possible in theory, but impossible to use. They collapse, they violate thermodynamics, they shred the traveller into dust finer than time itself, and yet they remain persistent, seductive, necessary. Because within their impossibility lies everything we do not yet understand about the universe. They are paradoxes made visible, the geometry of a question still waiting for its answer. Perhaps that is their true purpose, not as pathways through space, but as mirrors reflecting our desire to transcend it. For in every equation that forbids them, there lingers a whisper that says not yet. Sometimes science moves forward not by equations, but by imagination. In the late 20th century, when wormholes had long been dismissed as mathematical curiosities, It was not a physicist who reopened the discussion, it was a storyteller. Carl Sagan, writing his 1985 novel Contact, wanted his protagonist to travel across the galaxy in a scientifically credible way. He called his friend Kip Thorne, a theoretical physicist at Caltech, and asked a simple, dangerous question. Could we make a wormhole that someone could actually go through? Thorne had studied relativity for decades. He knew the rules, the prohibitions, the collapses that haunted every attempt at traversability. But something about the question lingered. He began to wonder, what if the answer wasn't no, but not yet? That question changed everything. Because Sagan's fiction gave Thorne a reason to do what pure science never would, to imagine possibility first and justification later. For the first time, a physicist began to treat the wormhole not as an abstract structure, but as an engineering challenge. Not, is it real, but what would it take? The conversation between artist and scientist bridged the gap between dream and discipline, and from that unlikely seed, a new field of study was born: traversable wormholes that might, under extraordinary conditions, remain open long enough for matter, or even people, to pass through. In that moment, science fiction did what it has always done best. It asked the question the universe is too silent to answer. Thorne's challenge was to find a loophole within Einstein's machine. Relativity allowed wormholes, yes, but it also destroyed them. Every simulation showed collapse the instant matter tried to pass through. So Thorne and his students reversed the process. They began not with the equations of gravity, but with the geometry of hope. What would a stable wormhole look like? How could its throat remain open without tearing? And what kind of matter would be needed to hold it that way? Their models revealed a strange possibility. A wormhole could in principle remain open if its interior curvature were balanced by a force pushing outward, something to resist gravity's crush. But ordinary matter could not do that. Every known form of mass attracts. To keep the tunnel open, one would need the opposite something that repels. The conclusion was astonishing and unsettling. To make a traversable wormhole, you would need negative mass. Such matter would behave in ways that seemed to mock intuition. It would not fall downward, but upward. Push it, and it would accelerate toward you instead of away. It would have gravitational repulsion, a literal inversion of the familiar. Einstein's equations permitted it. Nature so far had not revealed it. Still, Thorne followed the trail. He used the full machinery of general relativity, inputting the geometry of a stable wormhole and solving for what kind of energy would make it possible. The equations did not blink. They returned a clear answer: this bridge could exist, but only if filled with exotic matter with negative energy density capable of pushing instead of pulling. In 1988, Thorne and his collaborators published the now famous paper Wormholes, Time Machines, and the Weak Energy Condition. It was more than mathematics, it was a statement of defiance. It said perhaps the universe is more flexible than we think. Exotic matter sounds like science fiction, and it is in a sense. But in physics, the term refers not to imagination, but to anything that violates the energy conditions normally obeyed by all matter. These conditions, like the weak energy condition, state that energy density must always be positive for any observer. They are the moral code of the cosmos, ensuring that gravity always attracts, never repels. Thorne's wormholes demanded heresy, a violation of that code. They required pockets of spacetime filled with energy that behaved oppositely, repulsive fields that could keep the tunnel open, holding the throat against collapse. What could create such an inversion? Thorne turned to quantum physics for help. And there, in the strange behavior of the vacuum, he found a clue. In quantum theory, the vacuum is not empty. It seethes with fluctuations, pairs of virtual particles that appear and vanish, borrowing energy from nothing existing, for the briefest instants allowed by uncertainty. Between two closely spaced metal plates, these fluctuations are restricted. Fewer quantum waves can exist between them than outside. This imbalance creates a pressure difference, a subtle pull known as the Casimir effect. And that pull, when measured, behaves as though the space between the plates has negative energy density. It is not exotic matter in bulk, but it is proof that negative energy can exist fleetingly, conditionally within the quantum rules. Thorne realized the significance. If quantum fields could produce small amounts of negative energy, perhaps in theory, an advanced civilization could amplify the effect sustaining it across the throat of a wormhole. The bridge could remain open, its interior propped up by the repulsive pressure of exotic matter. Of course, no one had ever generated negative energy on a macroscopic scale. No one knew whether the universe would allow it beyond the quantum realm. But the principle was there, shimmering like a mirage. The equations of relativity and the laws of quantum theory were no longer enemies. Together they formed a loophole, a narrow space between impossible and not yet. The idea of negative mass thrilled the imagination and horrified the cautious. Because if it existed, it would not merely bend physics, it would rewrite it. Negative mass would repel normal matter but attract other negative mass. Two objects of opposite sign could in theory accelerate infinitely, without expending energy, chasing each other endlessly, through space violating the principle of conservation of momentum. If such material existed in abundance, it could destabilize entire galaxies or cause runaway feedback loops that would tear the universe apart. Physics, like nature, prefers balance. The introduction of negative mass would unbalance everything, and so the universe seems to hide it, perhaps not forbidding it outright, but sequestering it behind conditions too extreme for us to reach. Still, Thorne's thought experiment stood. He had not claimed to build a wormhole only to show that the laws of physics interpreted generously did not forbid it. That distinction between impossible and improbable changed the landscape of modern cosmology. It gave rise to new generations of questions. If exotic matter could exist, where might we find it? Could it be hidden in dark energy? The mysterious force accelerating cosmic expansion? Could quantum vacuum fields properly manipulated yield usable quantities of negative energy? And if not, could we someday simulate its effects, bending space-time artificially the way we already bend light? Each question led deeper into the frontier, where relativity meets quantum mechanics, a borderland of paradox and beauty where gravity ceases to be a pull and becomes a conversation. Kip Thorne's work did not prove that wormholes exist. It proved that the universe, vast as it is, still leaves room for daring questions, and sometimes that is enough. Every great theory begins as a refusal to accept that the limits we see are final. The story of exotic matter is that kind of refusal. It says perhaps what we call forbidden is only what we haven't yet learned to balance. Maybe the universe is not stingy with its wonders. Maybe it simply wants us to ask more carefully. In the quiet of his later years, Thorne would say that wormholes remain a useful fiction, not because they are false, but because they teach us where the edges of truth lie. To seek exotic matter is to confront the possibility that the cosmos itself might be stranger than our need for order, that even the laws of physics might contain mercy, and that one day, if we listen long enough, space may yet show us how to open its folded hands. In the quiet of an empty lab, two polished metal plates stand face to face. Between them nothing. No air, no light, no sound, only vacuum. But the vacuum, as quantum physics teaches us, is never truly empty. It breathes. Invisible waves ripple through it, fluctuations of electric and magnetic fields rising and fading in an endless dance. These are the whispers of the quantum world, the background hum of existence itself. Now place the plates close enough together, a fraction of a micron apart, and something strange happens. The space between them no longer allows all possible fluctuations. Only waves that fit can exist there while the rest are excluded. Outside, the quantum sea remains full. Inside, it is quieter. The difference in pressure pushes the plates toward each other. This invisible force, discovered by Hendrik Casimir in 1948, was one of the most delicate miracles of modern physics. It proved that even the void has structure, that nothing is in truth alive, and the energy inside that narrow gap behaves as though it were negative. Not merely less than normal, but below the baseline of vacuum itself. This, the physicists realized, was the first real glimpse of negative energy density, the kind of energy Kip Thorne's wormholes would require to stay open. It was small, unimaginably small, but it existed, and that was enough. The Casimir effect showed that the universe allows exceptions, that within the smallest folds of reality the impossible can briefly become true, and in that truth the idea of the wormhole found new life. In classical physics, energy is always positive. It fuels it, builds it, burns. But quantum mechanics whispers of another kind energy that subtracts instead of adds, that pulls rather than pushes. To understand it, imagine the vacuum not as absence but as an ocean of restless waves. Each wave has a tiny amount of energy, half a quantum trembling just above zero. When space is altered by matter fields or boundaries, these waves rearrange themselves, and sometimes their combined energy dips below the level of emptiness. That dip is what we call negative energy. It is a real quantity measurable through the Casimir effect, observable through the tiny shifts in atomic transitions, and possibly detectable in the behavior of black hole radiation. According to Stephen Hawking, the edges of a black hole at its event horizon can separate pairs of virtual particles. One particle escapes as radiation. Its partner carrying negative energy falls inward, reducing the black hole's mass. This process, now known as Hawking radiation, is built on the same principle space itself can generate regions of negative energy to preserve balance. The implication is profound. The universe already creates negative energy, though fleetingly and in minute amounts. It does so to maintain equilibrium between what is observed and what is hidden, between creation and annihilation, between what falls in and what escapes. For physicists like Thorne, this was a beacon. If negative energy naturally arises at the boundaries of horizons, could a wormhole be stabilized by harnessing the same principle? Could we one day shape the quantum vacuum guiding its fluctuations to build a bridge rather than a barrier? No one knows, but in the language of quantum fields, such a thought is not fantasy. It is possibility waiting for precision. The idea was as elegant as it was fragile. If a wormhole is a tunnel that wants to collapse, and negative energy is a pressure that pushes outward, then perhaps one could balance the two. Kip Thorne and his collaborators ran the equations. They imagined threading the throat of a wormhole with a skin of negative energy, a quantum scaffold to resist gravity's inward pull. If the pressure were strong enough, if the distribution were perfectly symmetric, the geometry could in theory remain open. The result was breathtaking. For the first time, the mathematics of general relativity and the strangeness of quantum field theory joined hands. One described the curvature of spacetime, the other the trembling of its smallest parts. Together they hinted at a loophole, a wormhole stabilized by quantum vacuum, a bridge suspended by nothingness itself. To keep it open, though, required a staggering amount of negative energy, far more than the Casimir plates could ever produce. The throat would need to be bathed in exotic fields, sustained by fluctuations on scales we cannot yet manipulate. It would be an engineering feat beyond any civilization we know, and yet the vision persisted. It offered something rare in physics, a reason to wonder without despair. Because the math did not say impossible, it said only not yet within reach. In the quiet corners of theoretical labs, scientists still model such structures, numerical wormholes that shimmer in simulation, their throats rippling with artificial Casimir pressure, their mouths gently pulsing like the breath of space-time. Whether they exist in reality is unknown, but even their hypothetical existence has value. They serve as test beds, laboratories of thought for the deepest theories of gravity and quantum mechanics, where the limits of both are stretched to breaking. As Thorne once said, even if we never cross a wormhole, understanding why we can't will teach us more about what spacetime truly is. Physics, like any great story, has its laws, and those laws are guarded by conditions, the energy conditions, rules, that tell the universe what forms of energy are allowed to exist. The weak energy condition, WEC, states that for any observer, the measured energy density must be non-negative. In other words, no matter how you move, you can never see less than nothing. It's a safeguard, a way of ensuring that gravity always attracts that cause, always precedes effect, that the fabric of spacetime doesn't tear itself apart. But the Casimir effect quietly breaks this rule, not globally but locally. Between the plates, the energy density dips below zero. The violation is small and fleeting, but it proves that the conditions are not sacred. If the WEC can be violated in principle, then perhaps nature is more lenient than we thought. Perhaps under certain geometries, curved spacetimes, strong quantum fields, the universe tolerates small patches of impossible physics so long as the balance is restored elsewhere. Physicists call this quantum inequality. It is a limit on how much negative energy can exist, and for how long before the universe demands repayment. You can borrow against reality, but only briefly and never without interest. This insight transformed wormhole research. It suggested that while a stable macroscopic wormhole may never exist, transient microscopic ones might blinking into and out of being like subatomic sparks. They could serve as shortcuts for information, as quantum threads, weaving the very texture of spacetime itself. And so the idea of quantum foam, a seething underlayer of spacetime at the Planck scale, emerged as the next great frontier. Perhaps the universe is not smooth at all, but a boiling sea of ephemeral connections, each one a whisper of a wormhole too small to see. In that sense, the dream of travel through spacetime never died. It merely changed scale, from the cosmic to the quantum, from the visible to the invisible, from certainty to wonder. In every law there hides a question, and in every prohibition there may lie permission written in smaller print. Negative energy is that small print. It is the footnote of the universe, a reminder that even the strictest rules have moments of hesitation. Perhaps that is the true lesson of the Casimir effect and Thorne's equations, that the void is not silent, that nothingness itself hums with the potential for creation. Maybe one day those whispers will become bridges. Maybe long after we're gone, another mind will learn to hold the vacuum in its hands and coax it to open, not through force, but through understanding. Until then, we are left with awe and the knowledge that even within emptiness there is still a pulse. If a wormhole could truly remain open, it would not only link places, it would link times. One mouth could be accelerated near the speed of light where time slows, while the other remains still. When reunited, they would be desynchronized, a bridge not across space but across moments. A traveller stepping through could arrive before they left, rewriting causality itself. Yet with that wonder comes danger paradoxes that logic cannot contain. What happens if you destroy the machine that brought you here? Can the universe allow contradictions to exist? Physicist Igor Novikov believed not. His principle of self-consistency suggests that the timeline would bend but never break every event. Even a journey to the past must fulfill itself. Stephen Hawking went further, proposing the chronology protection conjecture, an invisible safeguard preventing closed time loops, a cosmic sensor protecting cause and effect. Still in the silent equations of quantum gravity, wormholes remain tricksters' tunnels that could open not only to another world but to another version of the same one. Whether they offer escape or entrapment, no one knows. But perhaps the truest warning is this: every path through time is also a mirror, and sometimes what waits on the other side is us. In the end, wormholes remain suspended between theory and myth, allowed by Einstein's equations, forbidden by nature's caution. The latest research like that of 2019 even suggests that non-exotic wormholes could exist, yet they would be so slow, so inefficient, that crossing them would take longer than the journey through normal space. Elegant, but useless. Still, their true value lies not in travel but in understanding. They force physics to confront its boundaries, to test how far space-time can bend before breaking. Perhaps wormholes will never carry travellers, but they already carry ideas threading gravity, with quantum mechanics weaving imagination into mathematics. As Stephen Hawking once said, the universe is not only stranger than we imagine, it is stranger than we can imagine. And maybe that is enough to know that somewhere within the darkness of possibility, the cosmos is still dreaming of its own shortcuts. And so the story closes where it began, in the dark, infinite silence between stars. We set out to ask whether humanity could ever cross to the far side of the universe, and found that the real journey was never across distance, but across understanding. Every failed equation, every forbidden law, every fleeting glimpse of negative energy, all are steps toward a deeper truth that the universe resists, not because it is cruel, but because it is precise. It guards its mysteries the way an ancient library guards its oldest book, allowing only those who read with reverence to turn the next page. Perhaps one day a mind far wiser than ours will find the bridge hidden in that silence. Until then, we listen to the hum of the vacuum, the murmur of gravity, the faint rhythm of time folding into itself. For somewhere beyond the horizon of what we know, the universe is still whispering, "Not yet."